Good afternoon, everyone. We are welcoming today Professor Rebecca Lindsey. She is an assistant professor at the University of Michigan, United States, since 2022. She got her bachelor degree in chemical engineering from Wayne State University in 2010, her master's in chemical physics from University of Minnesota in 2012, and her PhD also in chemical physics from University of Minnesota in 2016. Her research group's interest is chemistry and multiscale systems and material evolution under extreme and dynamically changing conditions using advanced simulations and machine learning. So once again, thank you, Professor Lindsey, for being here. Feel free to share your screen and start your presentation.
Well, thank you so much for the introduction, and it's great to see you again.
Great to see you.
It's an honor to be invited among this panel of speakers. I was looking through the history of other Atom Seminar speakers, and it's just a fantastic lineup that you've had. All right, so why don't we jump in? So today I would like to talk about some of my group's efforts toward trying to use machine learning as a tool for understanding and simulating complex systems. I have reacting systems here because that's sort of the space that we tend to focus on. Before I dive in, though, I want to take just a couple of minutes to introduce my group to you all, since we haven't really had a chance to meet, and it sort of contextualizes the approaches that we take to our research. So in my group, one of the main thrusts that we have is the following. We like to use atomistic simulation tools, develop those tools, and develop machine learning-based tools to try to study the fundamental behavior under extreme temperature and pressure conditions. And so when I talk about extreme conditions, think the sort of temperatures and pressures you might see during a detonation, during impact of comets with celestial bodies, and within the cores of planets. So we're talking 1,000 to maybe 10,000 Kelvin in temperature, and tens to perhaps hundreds of gigapascals in pressures. And so then once we have this sort of fundamental understanding of how materials behave under these conditions, we like to use that and exploit it to try to understand and advance material synthesis capabilities. So here we're highlighting things like additive manufacturing. So this is how we 3D print metals using laser powder bed fusion, electron beam, ion beam, and laser-based modification of materials, sonication, and so on. And then also to try to design new materials or discover new materials. And so in short, my group really lives in a very cross-disciplinary space at the interface of chemistry, material science, and physics and engineering. So irrespective of whether you're focusing on materials under extreme conditions or just in general interested in studying complex, inherently multi-scale reacting systems, the simulations that you might use to probe those sorts of systems and the phenomena that take place within them is very difficult. And so in particular, we in our group like to use simulations to try to understand structure and dynamics and speciation and kinetics as materials evolve under these high temperature and pressure conditions, which at the very least means that we need models that are able to do a few things. We need to, of course, be able to describe chemistry, as materials tend to be highly reactive under these sorts of conditions. And yes, we need our models to work under high temperature and pressure. But what might be a little bit less obvious is that we also need our models to work on rather large spatiotemporal scales. And so to give you a sense for this, I'm showing one of my favorite example images that I stole from one of my former colleagues, where in this picture, what we're looking at up top here is a molecular crystal of an explosive material. And what he's done in this simulation is he has imparted a shock wave from the left side of this material that has passed through. And so out on the side, you can see that that's where the shock front is. And so the practical effect of this, it's like he took this molecular crystal and smacked it really hard. And so once the shock wave passes through this material, you can see these yellow striations that are left behind. These are nominal shear bands, which are localized regions of increased disorder, which happen to also be thermally activated. And so it is within these features that the chemistry that ultimately gives rise to detonation of this material begins. And so if one wants to study that process and understand what makes some materials more sensitive than others, more dangerous to work with than others, we really need simulations that can get out to these sorts of scales, which to quantify for you, this is about 90 nanometers in the transverse directions, and we're about 160 nanometers in this longitudinal direction. And at the same time, we need models that can faithfully describe the chemistry that happens within these features. And so think quantum accuracy on large scales is really what we're looking for. And so at the start of the work that I'm going to talk about today, we really had two choices available to us in terms of the sorts of models that we could use. We could either use these quantum-based techniques, so things like density functional theory and so on, where these are very predictive methods, so very powerful in that sense. But the problem is that they're also very computationally expensive. So we can really only think about simulating a few, maybe tens or maybe a few hundreds of atoms. And so then on the other hand, we have these sort of classical, conventional reactive interatomic models. So think reactive force fields, something like REACT-FF, for example, where by design, these models can design or describe chemistry, and they are very computationally efficient, so they can easily get out to these sort of target scales over here. But the problem is a few-fold. So first, their underlying form is generally not designed for describing systems under very high temperature and pressure, so you might need to modify some of what underlies those equations. And even ignoring that, they're generally not parameterized for the materials or the systems that we want to study. And the very complex and highly nonlinear form that these models take on make generating new parameter sets a significant challenge. And so we were really left with this capability gap. What we really wanted was a method that could give us the predictive power of quantum mechanics with a method that has computational efficiency closer to these conventional reactive interatomic models. And so that drove us to become interested in developing machine-learned interatomic models to try to bridge this capability gap. Okay, so you all at this point have probably heard of machine learning models before, but I want to take a couple of minutes just to kind of make sure that we're all going to start at the same level of understanding before I jump into the rest of this presentation. So in order to understand what a machine learning model is, I find it easiest to start with what a classical molecular mechanics model is, because that's something that we all know and love, at least to some extent. And so the question that I want to answer here is, how does one develop a molecular mechanics model? And so typically the way this is going to start out is we're going to think very deeply about the system that we want to describe and ask ourselves, okay, what are the key equations that I can write down that I think capture the underlying physics of the system and the evolution of that system that I want to describe? And so then once we have that underlying functional form, that set of equations, we're going to fit the parameters for those equations through parameter sensitivity studies. So we're going to make an initial guess for those parameters, we'll simulate with our model, and predict some properties. Maybe these are boiling points or densities or surface tensions, something like that. We'll compare with some validation data. And if our predictions don't match, we're going to go back, tweak our parameters, and try again, iterating through this until we get a model that gives us the prediction that we want. And so the key here is that in these molecular mechanics models, we are making assumptions about the key physics that govern system evolution, and we are, with that fixed functional form, going to force that model to give us the predictions that we want by tuning the parameters of that model. So machine learning models work in a very different way. Instead, what we're going to do with these models is give our fitting framework a very flexible set of basis functions, and then we are going to give it lots and lots and lots of training data. And so our machine learning framework is going to inspect all of this training data, and it's going to use those basis functions that we gave it to try to construct what it thinks potential energy surface topography should be to give us simulations that generate equivalent data to what we have in our training sets. And so the key difference relative to these molecular mechanics models is that these machine learned interatomic models are going to try to figure out for us at sort of a high level what the key physics are for the system. So we don't necessarily need to know that a priori. And in that sense, it's a very flexible framework. It's really great for when you're studying complicated systems for which we don't know how to write down an underlying model. So there are a multitude of different ways that you can generate these machine learning models. But today, I want to talk a little bit about the unique framework that our group has come up with. So in particular, if you have heard about machine learning models before, you've probably heard about them within the context of neural network-based potentials. That is certainly one way to go about this, but we've taken a rather different approach, where our approach was really informed by a very specific target application. We wanted to be able to use these machine learning models to describe complicated condensed phase chemistry in materials evolving under very high temperatures and pressures. And so the approach that we came up with, we call CHIMES for the Chebyshev interaction model for efficient simulations. And so we're going to perhaps describe these models as physics-informed machine learning models, and I'll explain why in just a moment. So we start off by saying that we generally believe in the many-body cluster expansion. So we're going to describe our total system energy as the sum of energies for dimers and trimers and tetramers of atoms up to arbitrary bodiedness. And we're going to use the following generating function to write down these many-body interaction terms. And so this equation here might look like a little bit of a discrete mathematics mess, but it is telling us really just the two key ingredients of a CHIMES model. The first, highlighted in this orange, is that our flexible basis functions are Chebyshev polynomials. And then in purple, we have the second ingredient, which is telling us when we describe many-body interactions, we're going to treat them as the product of interactions for constituent atom pairs. So for something simple like a two-body interaction, we only have a single pair type, IJ. And so this expression up here reduces to the following, where each one of these t's is a polynomial of the subscripted order. The argument s is a transformation of the distance between our atoms, I and j. So this is essentially a symmetry function if you've heard of those before. And then the coefficients out front are the parameters of the model that we are trying to figure out when we fit them. And so then for something a little bit more complicated, so for example, a three-body interaction, we now have three atom types, I, J, and K. And so that means we're going to have three pairs of atoms, IJ, IK, JK. And so coming back to this generating function, this expression is telling us that that means that we're going to have three of each ingredient. And so whereas in the two-body case, we had a single sum over the order of our polynomial for our single pair interaction, for the three-body case, we get a triple sum over the polynomial order for our IJ polynomial, our IK, and our JK polynomial. And then you'll see that for each term in this triple sum, we have a single parameter, single coefficient here. So I want to pause and make just a couple of observations. The first thing is a special observation for any of you that might work in this space or use machine learning interatomic models. One of the things beyond the fact that we are not using this sort of neural network formulation that most of these models use that makes us unique is how we define our clusters. So the vast majority of models out there use an atom-centered descriptor. We use a cluster-centered descriptor. And so practically that means that our models are very conducive to describing molecular geometries, the geometries of reacting molecules, and so on. You'll also see that I've said before, are a physics-informed model. And so again, you see some of that in our choice of this many-body cluster expansion. Some of it's hidden in here. So these symmetry functions that we use impose things that we know to generally be true about systems. So in particular, as you take atoms and you move them apart, we know that generally speaking, the energy or the strength of that interaction is going to decrease. So we bake some of that into our models, but at the same time, through this polynomial expansion, still afford the flexibility that we really need for our models to be powerful in their ability to describe our target potential energy surfaces. And then the last thing I want to point out here is that our models are completely linear in the parameters that we're fitting. So these coefficients C that you see over here and down here. And we'll see in just a moment why that is such a convenient feature to have. Okay, so we know why we developed this framework. We've seen what these models look like. So the next question is, how do we fit them? And so at the simplest, this is done through a nominal force matching framework. And so the way that this works is we are going to start off by running short first principles, so quantum-based simulations for our target systems and conditions. And that's going to give us a bunch of simulation trajectories from which we're going to take a couple of snapshots, a couple of frames. And each one of those frames will tell us the position of our atoms, the corresponding forces, and if we ask for it, the energy and the stress tensor for that configuration. So that's what our training data looks like. And then we're going to fit our models by minimizing an objective function of the following form, where all this is saying is that, for example, we want the force on each atom, lost my cursor, the force on each atom subject or predicted by our quantum-based reference method, and the force predicted by CHIMES subject to our fitting coefficient to be as close as possible. Where, because our models are parametrically linear, we can just rewrite this in the following matrix form, and now we are free to use our favorite advanced linear solvers that can do things like regularization, feature selection for us, but perhaps most importantly, are very quick to run relative to, let's say, a global optimization method. So from all of this, really, though, the takeaway is that by design, these models are rapidly parameterizable, so we can fit them very quickly, and they're capable of, I have in quotations, quantum accuracy. So they can be quantum accurate, but of course, there are always some stipulations there. Okay, so we know what this model looks like. We know how it's fit. So what do I really mean by quantum accuracy? So let's explore this. So I want to provide an example of how accurate our models can be within the context of a recently developed model for carbon. And so this is a deceptively complicated system. In particular, we wanted our model to work from nominal ambient conditions, so 300 K and a low pressure, all the way up to about 10,000 Kelvin and 100 gigapascals. And so that means we need to be able to recover graphite at various different pressures, diamond at different pressures, molten carbon, phase transformations between them, and so on. So, okay, how do we do? Well, when we generate our models, one of the first questions we ask is whether we can recover the data that we fit to. And so what I'm showing here are called parity plots, where the way that you read these is that the x-axis on any one of these plots is going to be a property, so stress, force, or energy, predicted by our quantum-based reference method. So for us, this is going to be density functional theory. And then on the y-axis, it's the prediction that we get for CHIMES for the exact same input. And so a perfect model is going to fall on that dashed diagonal line. So that's what we're looking for. And you can see that our model is doing quite well in terms of this metric of accuracy. However, these sort of numerical metrics, these root mean square error type descriptions of model performance are insufficient to really say whether a model is good. And so, in fact, you can see models that look like they're doing great in this sort of metric, but when you go to use them in a simulation, you'll find that they exhibit unphysical behavior, or maybe they preclude conservation of your conserved quantity, and so on. And so it is absolutely imperative to validate these things on the basis of physical properties. So let's take a look at how that can go. So what I'm showing here are radial pair distribution functions. Oops. In this column over here, and then the corresponding vibrational power spectra. So those are over here for carbon at a multitude of different temperatures and pressures and phases. Over here, we have the same thing. This is for another set of simulations, radial pair distribution functions and vibrational power spectra. So we have here diamond at about 3,000 Kelvin. We have graphite at two different temperatures, 1,500 and 3,000 Kelvin. We have carbine down here, and then these here are all for molten carbon over a variety of different temperatures and pressures. And the way that you read this is that the blue data is from DFT, and the dashed orange data are from our models. And so again, you can see that we have pretty good agreement with our target DFT data. And we can kind of keep going with this. So over here, we are looking at predicted pressures for each one of these state points that we see the RDFs and the radial the RDFs and the vibrational power spectra for. We have the diffusion coefficients for all of those simulations. And then these two plots here are asking if I take the crystal structure of diamond and graphite and I compress it by some amount, how much does, or I impose some pressure on it, how does the volume of that system change? And so again, blue data is DFT, orange is CHIMES. And in all these cases, you can see that we're doing a pretty good job with some outliers, in particular this guy over here and this one over here, which I'll just say is due to a design decision. And so in particular, in graphite, the interlayer spacing is determined by a very long-range, weak dispersion interaction. And because we want to be able to simulate very, very large system sizes, we decided to use a cutoff for our model that's a little bit too short to get that interlayer spacing perfectly. And so that's the origin of this deviation here. And so with that caveat out of the way, though, we can see that we're able to generate very accurate models with relative ease through this framework, even for complicated systems like this. So hopefully now you kind of believe all the stuff that we talked about in the previous section about, you know, what we can really do with these CHIMES models. Okay. So one other point I want to make is that there's a multitude of different ways to use this framework. So far we've talked about using CHIMES as essentially its own standalone model. So if I want to simulate a system, I use CHIMES as the model to describe all of my interactions. But you can also use it in so-called delta learning mode, which is just another way of saying that you can use CHIMES to correct some underlying form. And so in particular, your underlying model could be some full molecular mechanics model, so some force field you took out of the literature. You can do this with semi-empirical quantum methods as your underlying form. Maybe you just want to build a CHIMES model on top of some pre-existing electrostatic model, something like that. And so in our group, we are pretty fond of using CHIMES to correct density functional base type binding models. These are semi-empirical quantum methods. So essentially they pre-tabulate the Hamiltonian and they have self-consistent charges that allow you to approximate the performance of something like density functional theory, but it is orders of magnitude faster. So you can get to nanosecond timescales, albeit in the same system sizes. And so this is nice because we can probe problems where we do care about things like electronic structure, but we can do it rather efficiently. And so I just have two examples of work that we've done on this. So in this case over here, we use CHIMES to correct density functional base type binding to generate a generalized organic material model for gas phase chemistry. And so in this case, we took a pre-existing data set. So this ANI 1X training set, I think there's 5 million different molecular configurations in it. It's a pretty famous data set that was used to generate the ANI 1X model, which is also a very famous machine learning model. And really the takeaway here is that when we do this CHIMES as a correction, we need way less training data than you would need for a standalone model. And so in this case, you can see the sort of accuracy that we were able to get using only 3% of the data that was needed to generate that full ANI model. So a pretty powerful thing. And so then one of the other interesting applications we've used this for was to try to understand hydriding in actinides. And so again, this is a sort of problem where you're going to want to use a first principles based approach. However, the different spin states the system can exist in makes converging those calculations very, very, very difficult. And so here we generated a CHIMES-corrected density functional base type binding model that allowed us to perform these nudged elastic band calculations and actually get the energetics for hydrogen adsorption into the material about 245 times faster than we could have if we were stuck with just DFT. So all in all, a pretty useful tool. Okay, so far I've kind of told you all the good things about these machine learning models. They're very easy to generate. They can describe really complex systems. They're very versatile, so forth and so on. But the fact of the matter is there are still many challenges that as a community we're trying to overcome, particularly as we think about applying these tools to complex systems. And so to give you a sense for this, I want to talk you through sort of the history of CHIMES, where we started and where we're going with it, and the sort of problems that we're thinking about now. And so Our effort started back in 2017 with what in hindsight was a very simple fitting problem. So we wanted to generate a model that worked for molten carbon at a single state point. And so that means we only cared about a single atom type, single state point. Our model only had up to 3 body interactions. And so it was 228 parameters in total. So for a machine learning model, that's very small. And the model only required 20 configurations from quantum mechanics to fit to. So that's less than a megabyte of training data. And so ignoring the time that went into developing this framework, coding everything up and running the quantum calculations, the models in this paper took less than 5 seconds to generate. So that seemed to work pretty well, and we were sort of spurred on by that success and started trying to apply CHIMES to systematically more complex problems. So for example, introducing an additional atom type so we can start to look at condensed phase molecular systems. We started looking then at chemical reactivity in these 2 atom type systems. Then we asked if we could do that over a broad range of temperatures and pressures, where for all of these problems that I like to think of as sort of intermediate complexity, we found that if we took the simple fitting approach that I described earlier in this talk, generate some training data, minimize objective function, get a parameter file, the models that we got out were very bad. So, okay, well, what's going on? Well, it comes down to the fact that training data generation remains one of the grand challenges in this area of machine learning model development. And the reason for this really comes down to how we generate this training data. So for applications like ours, the community tends to use first principles molecular dynamics simulations to generate our training data. And so practically, this means that our training set is going to have favorable regions of physicochemical space overrepresented in it. And so our models are going to do a very good job of describing those sorts of configurations, but it's not going to know how to describe, let's say, a barrier and a potential energy surface over a repulsive wall. Okay, how do we fix this? So we took a very simple approach. This is our naive iterative refinement framework over here, where the basic premise is the following. We're going to start off in the same way that we had before. So we'll generate some initial training set. We're going to fit a model with that training set, and then we can go on and simulate with that model. And so our first model is going to be bad, as we talked about before. That means it's going to sample some very weird configurations. And that's a good thing. We're going to take those strange configurations, we're going to send them to our quantum-based reference method to see what quantum thinks that the forces and energies and stresses for that configuration should be. We add that new data to our training set and generate a new model. And so now in this next iteration, our model has learned from its past mistakes. And so now it knows how to describe these stranger regions of the potential energy surface that typically, again, correspond to barriers, repulsive walls, and so on. And so in some sense, you can think of this as a very naive enhanced sampling technique to increase the diversity of the data in our training sets. Okay, so that worked pretty well for these intermediate complexity problems, which brings us to the sorts of things that we're working on today. So one of the current initiatives in my group is to develop a generalized organic materials model that works from ambient conditions all the way out to our extreme conditions of, again, 10,000 Kelvin and 100 or so gigapascals. Where now, if we compare this to our carbon example, way at the bottom of this plot over here, now we're talking about 4 different atom types. We want this to work over many different state points. We might need to go up to 5 body interactions. We're still figuring that out now. And so by back of the envelope calculation, this means that we'll probably need on the order of, let me get my laser pointer going. We'll probably need on the order of 10 to the 5th parameters, necessitating more than a terabyte of quantum-based training data. And so that brings with it some practical questions. First things first, oops, wrong way. How do we even generate that much training data? And how do we make sure that the data that we're generating is meaningful? Can we accelerate this process in some way? And then there's these more subtle questions, which are, say that I want to develop these models to describe a process that has characteristic time or length scales that exceed what's accessible by our quantum-based reference method. How do I generate data that can help teach the model how to describe those sorts of problems? And more importantly, how do I validate the predictions that I get from my simulations? And so these are the sort of things that we're thinking about right now that are really driving us to develop more intelligent tools for model generation. And so I'm going to just give you a sort of quick survey of some of the things that we're working on, and then spend the rest of my talk giving you a sample application of what we can do with these sorts of tools insofar as actual scientific studies. Okay, so there's sort of three thrusts that we have been working on to enhance our model's abilities to describe these complex systems. One of them is multi-fidelity model development. And so here the idea is the following. Typically, when we generate one of our CHIMES models, we're going to use just our quantum-based training data. But what if we could use some cheaper method like density functional based tight binding? And we can use this to supplement our quantum-based training set to generate this model more efficiently. And then maybe we want to go up to the next level. Maybe we would like to generate a coarse grain model. Can we pull together data from our quantum-based method, our density functional based method, and CHIMES again to make this process much more efficient? So that's one thrust we're working on. We're also working on active learning. So this is basically a concept where we want to be able to increase the information that is contained in our training sets while keeping the overall size minimal. The idea being that generating training data is expensive, right? Running quantum calculations takes a lot of computational resources. And so what I'm showing here is a schematic of one of the active learning frameworks that we came up with that is designed to enhance the accuracy with which models can describe condensed phase chemistry. And then over here, another thing that we're thinking about is transfer learning. And so what I'm showing is the hierarchy of parameters if you want to generate a CHIMES model that can describe carbon, hydrogen, oxygen, and nitrogen containing systems. Currently, we and pretty much every other person that works in this machine learning model development field will generate this model by trying to fit all of these parameter blocks at the same time. So coming back to our previous discussion, that's our order 10 to the 5th parameters we're going to try to fit all at once. For other machine learning models, this is done by necessity. For our models, though, there is something unique about our underlying form that allows us to actually break this fitting problem down into individual blocks that we can fit on their own and combine later. So you can think like a model that works like Legos. And so in addition to allowing us to more efficiently generate these parameters and more effectively validate the parameters, the other implication is that our models are explicitly chemically extensible. So if I want to add another atom type to my C, H, O, and N, I don't need to refit anything. I just need to add some more parameter blocks to the side of this hierarchy. So those are some of the things that we have going on right now. Okay, so 2 more points that I would like to make. So one of them is, I motivated a lot of our work talking about how we care about materials under extreme conditions, which might seem rather unrelated to the application space that you care about. But one thing I want to be clear about is that CHIMES itself is application agnostic. It can be applied to any sort of problem in particle-based simulation. And so this is just a survey of some of the things that we have used this for, which span from, again, looking at the structure of ambient water to developing coarse grain models for inverse design. So again, there's a lot of different things that we can do with this tool. But perhaps most importantly is the following. As somebody who works in method development and model development, it can be easy to get caught up in just how fun it is to develop these tools. And you might find yourself focusing on problems that are interesting from the methodological development standpoint, but maybe not pushing the, let's say, application science forward. And I want to be clear that CHIMES is actually helping us push that application science forward as well, or worded otherwise, allowing us to start to push into some previously inaccessible problem spaces. And so what I'm showing here on the right are snapshots from some of our simulations, which are the first direct shock simulations of an explosive compound using a fully atomistic machine learning model. So what we're looking at here is what happens when you take hydrozoic acid and you essentially shock it, so you smack it really hard. This is an important question because hydrozoic acid is frequently used in the synthesis of azides, but it's very dangerous to work with. So again, if you drop your vial, it might explode. And this has happened in like organic synthesis labs before. And the scary thing about this material is if you accidentally do something like introduce bubbles into your fluid, it becomes more sensitive. So this is something that we know about, but is not something that people want to characterize because it's a scary experiment. And so we're able to use simulations to probe these sorts of questions. So here you can see our unshocked liquid in green. We've got a bubble in the center, and you can see our shockwave moving through. Once the shockwave passes through, you can see that that bubble region is essentially it's a hot spot. So that's where our chemistry is going to start and where our sensitization comes from. And so then over here, these are simulations. These were the first simulations of a shockwave-driven nanocarbon synthesis process done on overlapping scales with experiment. And in my unbiased opinion, this is a really cool effort. And so I want to spend the rest of my talk kind of just giving you a highlight overview of this work. Okay, so let's switch gears. So the story that I want to tell, I've called a joint simulation and experimental study of shockwave-driven carbon condensation. And I want to start off this story by answering the question of what the heck is this and why should anyone care? So let's dive in. So we've known since about the 1950s that if you take a carbon-rich material that lacks sufficient oxygen to undergo complete combustion, and you subject that material to strong shock waves by, for example, detonating that material. Oh no, it's frozen. There we go. You can form a variety of very interesting nanocarbon particulates. Oh no, my presentation's frozen. Let's see here. There we go. And so in particular, this combination of RDX and TNT shown here, when detonated, is known to form these beautiful nanodiamonds. And in fact, industrially, that's one of the ways that they're synthesized. This guy over here is called DNTF, and he makes these beautiful graphitic nanoions. And then this guy over here creates these amorphous nanocarbon particulates that agglomerate into these larger hierarchical structures that you can see in this image. And so beyond just kind of looking cool, it turns out that these materials have a myriad of different scientific and technological applications. Let's see here. So again, we talked about these nanodiamonds. One of the things that they're used for is coatings for things like saw blades to improve their durability. These graphitic materials are important for quantum computing applications, and both these nanodiamonds and amorphous carbon particulates are often used for drug delivery and bioimaging and so on. And so there's a lot of interest in this process because unlike other approaches for synthesizing these nanocarbon materials, with shockwave-driven synthesis, you get a lot of particles very, very rapidly. So it's a very high throughput technique. But the problem is, as you might have gathered looking at this image, it's a really complicated, really messy process that's not very well understood. And so one of the questions that we ask in our lab is whether we can sort of wrangle this process and achieve a tailored synthesis capability for carbon nanomaterials through shockwave synthesis. Okay, so let's see here. I mentioned that this is a process that is not very well understood, and the reason for this comes down to the associated time and length scales. So these particles can form in under 150 nanoseconds, and they're typically 2 to 10 nanometers in diameter. And so from the standpoint of our experimental colleagues, these are very, very tiny things that form very, very rapidly. So when they try to watch this process to learn about the kinetics or the mechanisms, they really just see two signals. They'll see a signal that says there are no condensates in the system, then they'll see a signal that says they have all finished forming. And so they can really only make estimates about the upper bound time it takes for these species to form, and they can't really say anything about how they form. Now, somewhat ironically for us atomistic modelers, these are humongous things that form over painfully long time and length scales, particularly when you consider that this is a condensed phase reaction-driven process. So we need very high accuracy reactive interatomic models to describe it. And then, when we talk about the kinetics of this process, we need to go large enough to be able to simulate populations of these nano-sized particles. And so this is a very expensive calculation that we need to do. And so we became interested in whether we could use CHIMES to try to enable some studies of this phenomena. But let's take a step back. So this process, as I said before, is messy, and there's a few reasons for this. First and foremost, the chemical complexity of this process is quite high. So you might be looking at this and thinking that these molecules don't look so bad relative to a protein or something like that. But once these guys start reacting, there is a manifold of chemistry that you need to sift through to really understand the governing mechanisms and kinetics for this process. Then there's other issues. So again, the current status of this sort of synthesis technique is to use detonation. And materials that detonate, so explosives, tend to exist in the solid state. And so now when we think about understanding how this process works, we need to think about material strength and defects and dislocations and all of that, which really complicate the picture. Finally, we have this issue that if we use an explosive compound, the source of the shock wave that ultimately drives the material to the high temperature and pressure that gives rise to formation of these nanoparticles is a characteristic of the material itself. And so if we really want to be able to achieve this tailored synthesis of these materials, we want to be able to do this in a non-detonating material. So this allows us to have complete control over the precursor chemistry and the shock properties. So how hot and how compressed do I make the system, over what time period, what does the quenching look like, and so on. At the same time, we want to try to do this in a simpler system, a chemically simpler system, so we can establish perhaps more fundamental but more broadly applicable insights into how this process works. And so we started by looking at this study by a pair of researchers named Nelson Ree from back in the 80s, where they took cryogenic carbon monoxide and they performed shock compression experiments on it. And this was interesting because it is the simplest possible material that can undergo this phenomena, carbon-rich and oxygen-deficient. And so what I'm showing here are data from their experiments. So these little crosses here are the measurements that they made. So essentially the way that you read this is as you shock the system harder, you're driving it up to higher pressure. And alongside their data, they drew these three curves that come from a theoretical equation of state model, which was a bit questionable in hindsight. But here we have the solid curve that is for a system that compresses but does not react. And then these two dashed curves are for systems that are allowed to compress and react and form equilibrium or quasi-equilibrium with graphite or diamond and graphite products. And what they see is that for their weaker shocks that fall at lower pressure, their data seems to be on this non-reacted curve. Whereas when they hit the system harder, their data seems to fall on this curve that accounts for formation of carbon-based products. And based on this said, well, maybe what's happening is I'm forming some sort of carbon clusters, some sort of nanocarbon particulates. But they never did any recovery experiments to actually validate that hypothesis. And so we asked, well, can we use CHIMES to study the system and see whether or not condensates form? And if they do, can we start to say something about how? And so we went through and developed a model. I'm not going to show the validation data for that in the interest of time, and just jump ahead to the simulations that we ran with it. So one of the first things that we did is ask what happens when we run our simulations at the quantum accessible size limit, and we just run it for a long time. And when we do that, we see not a lot's going on. It's nothing really happening there. But because our CHIMES models are computationally efficient relative to these quantum-based approaches, we can scale up to much larger system sizes. So in this case, we're over 1 million atoms. And so what you're looking at here, these red dots are oxygen atoms, and the correspondingly small black dots are carbon atoms. And you can see that we're forming these roughly 5 nanometer sized nanocarbon particulates over the half nanoseconds that the simulation is running for. And so this was a really exciting result because it seems as though we have predicted that in fact, these nanocarbon particulates can be formed by shock compressing cryogenic liquid carbon monoxide. But this naturally leads to the question of whether this is real or if this is an artifact of our model. Maybe the model's wrong, maybe there's an instability in the model that causes this to form. But we were fortunate enough to have some excellent experimental collaborators that developed a experimental platform that allowed them to probe the same precursor on the same time scales and overlapping length scales with our simulations. And so after we generated these predictions, they ran their experiments and were able to do recovery and characterization and found particulates that look like this. And so this little Pegasus-looking animal over here is comprised of these smaller particulates outlined in these red semicircles, which their experiments showed were comprised of they had the same chemical composition, the same size, the same shape, and they formed over the same timescales as our simulations predicted. And so we had this very compelling validation of our simulations that gave us the sort of green light to dig in and try to say something about how and why these things form. And so there are three questions that have stood since the 1950s surrounding this process. What does it even look like at a high level? How does chemistry factor in? And what are the overall kinetics for this process? We're frozen again. There we go. Okay, so from our simulations, we can start to answer these questions. So for example, here I'm showing a cluster growth timeline. So quite literally watching a cluster begin to form. So it's a little seed cluster all the way through its maturation to a nanoparticle. And so we can see it starts off relatively low density with oxygen distributed throughout. And as time goes on, it becomes denser and denser, pushing oxygen out to the exterior surface. So we can do analysis like this. As far as chemistry, one of the things that we can ask is, well, we know that these clusters grow by some shrinking and some growing, so an Ostwald ripening mechanism, but what does the carbon transport for that process look like? And so here we're going to track the single carbon atom. This movie's going to reset. You're going to see him start from down here. He's going to transport between this particle to this one. And you'll see that whenever this particle is close to the surface or outside of one of these clusters, it's always bonded to at least one or two oxygen atoms. And so we have a sort of reactive hitchhiking mechanism for transport of this carbon atom between these two clusters. So again, we can do analysis like this. And then for this last question about kinetics for this process, here we analyzed our simulation data through the lens of classical nucleation theory. And what we find, so in this plot, we're looking at how the Q average radius of gyration of our particle changes with time. And here we're looking at self-similarity of our cluster size distribution. And from this, our data tells us that this process does indeed follow classical nucleation. And so this is nice for pushing our predictions to even larger time and length scales through these kinetic models. And so really just to wrap this story up, these simulations allowed us to answer questions surrounding this process that have stood for nearly a century now. And so all in all, some pretty exciting work. So in the interest of time, I'm going to wrap things up there. I have some concluding remarks over on the left side of the screen, but also want to take some time to acknowledge I guess the contributors for this work. So I am actually just completing my first year as a assistant professor at Michigan. So this is my group. I'm super excited to be working with all of my wonderful students. Prior to working at Michigan, I worked at Lawrence Livermore National Lab. So these are my collaborators back there. The work that I talked about has been funded by the NNSA, the US Department of Energy, and the LDRD program that's part of Livermore Lab. And then finally, all of the software that we use to do all of the work that I talked about here is free and it's available on GitHub. We are always looking for people to test these tools for their special applications. So we do encourage you to do so. And if you run into questions, just reach out. We would be really happy to help you troubleshoot. So with that, I'll stop and would be happy to take any questions.